techniques. We have the multi-level binary techniques. This is where you probably have the, the positive and negative representations. We do have the biphase techniques and the scrambling techniques. So these are the four general groupings that we have. Now, and at each of these grouping, there is some type of scheme, or there's a given scheme that is being used, or they do have given schemes for the various groups that we have. When it comes to non-return to zero, we do have the non-return to zero level, and then the non-return to zero inverted. And then when it comes to the multi-level binary techniques, we have bipolar AMIs, or the bipolar alternate mark inversions, and the pseudoternaries. For the biphase technique, we do have Manchester and differential Manchester, very popular for data transmission. And then the scrambling techniques, they do incorporate a bit of the multi-level binary techniques, which is the bipolar with 8 zeros substitutions. We'll look at that later. A bit more complicated to get, usually adopted within the US market for CDMA transmissions. And then in Europe and Japan, they have the high density bipolar with 3 zeros. So this, I would probably say the scrambling techniques are more popular within the European and Western, either Western and other European countries, as well as the Asian market as well. Okay, for mostly communication transmissions that requires embedding various code elements within the transmission to make it much more uniform and much more easier to interpret, or much more efficient way to identify the issues that might affect the transmission levels. So now let's come back to the non-return to zero technique and look at some of the key schemes involved. So as we mentioned, we do have the non-return to zero level, which is usually a typical type of encoding scheme used to generate or interpret digital signals by terminals and other devices. Non-return to zero levels indicates that when the signal has a bit of sequence with a 1 or a 0. 1 is usually represented with a low voltage pulse, and 0 represented with a high voltage pulse. Let me actually move to a signal here so we can look at it very well. So maybe that would help us understand that. Because these are the theoretical representation or interpretations of them. Let's get a signal so we can identify that very quick. So here you do have the non-return to zero techniques with the first scheme, which is the non-return to zero level. If you notice, if you were to plot a non-return to zero level signal transmission, you do have a sequence of bits here, or a message here. This happens to be a message, by the way, which is in its digitized form, or in its binary sequence of either 0 1 0 0 1 1 0 0 0 1 1 1. Okay, so this could be information over here. It could be a character, it could be a sentence, a word, or whatever it is, or just a feed. Okay. Now, if one bit of that particular given sequence, the data sequence, it's that happens to have a zero binary digits or state within the non-return to zero level, it's represented in a graph to the plotting as a high voltage pulse. So over here you'd have let's say you can use a +5, which is generally what's being used for most transmissions within electronic devices. So a zero would be a high voltage pulse. This would be a zero here. Just know in terms of voltage wise, this is a +5 voltage, and then there's zero voltage, which is basically at a flat level. And if it goes below that, it becomes a minus. But within the non-return to zero, we don't really have some of these negative voltage representation as compared to the multi-level, which we'll look at a bit later. So you have the zero having a high voltage representation and one having a low voltage representation. So with that sequence, it's a lot easier. One of the reasons why they say the non-return to zero is the most easiest encoding technique to use for signaling or signal interpretations. And then the non-return to zero inverted does have a different form, and this is how it really works out. Zero, it's usually at the starting bit of the information being transmitted. It's considered a level voltage pulse or a low voltage pulse. You can interpret as a negative or whatever, but that's just like I said, as I mentioned earlier on, the whole concept, the whole wording of negative and voltage are just terms that are being used to interpret the various voltage fluctuation that we have. Okay, so keep that in mind. So with the non-return to zero inverted, a 0 bit is represented by a low voltage state, okay, and a 1 is represented by a high voltage state. By depending on the sequence of the bits being transmitted, when there's a transition within the bit levels, only the ones are actually interpreted with voltage transitions or signaling transition. So, like for instance, a 1 to 1 would mean a transition. Very good. But a 1 to 0, no transition. So keep that in mind. Very good. I've kind of put some of these things away to help you out in terms of the signaling of these two particular techniques that we have within the non-return to zero. So I indicated that you have a zero bit would be represented by a high voltage pulse, and a 1 is a level voltage pulse. But a non-return to zero inverted, you have a zero representing a level voltage pulse with a zero signal, and a 1 having a high voltage signal, but does have a transition when you do have 0 to 1 or 1 to 1. Okay, so keep that in mind. The key here are 0 to 1 and 1 to 1 are the levels that signal transitions a lot within the non-return to zero inverter, which means any other bit sequence would not require transition. You just basically stay at the very states that a signal was initially. So like for instance within this, if you notice, the first bit was 0, so we did have the 0 or level voltage pulse, and then the next bit was 1, so we moved to a high voltage pulse. Now the other bit after the 1, it's a 0, and looking at the transition points, we said that You only transition when you have a 0 to 1 or a 1 to 1. And since it's 1 to 0, it's not a 0 to 1 or a 1 to 1. We don't transition. We just basically stay at that particular, the same state that the sequence, the bits, the voltage pulse was at without any transition. But look at it very carefully again. When we got to from 0 to 1 with the transition, because it's part of the requirements for the inverter. So we did have a transition from a high voltage pulse to a low voltage pulse because we moved from 0 to 1. And then 1 to 1, obviously, same again, we transition from a low voltage pulse to a high voltage pulse. And then 1 to 0, there's no transition. But there would have been a transition, assuming that this was a 1. Then you'd have a drop down again. Okay? Now, so if assuming that you had a 1 here, and you have another 1 over here, then you transition again. Now, what if you had a 0 here? Oh, sorry, you had a 1 over here. You had a 1 here, and then you did have a 0 over here, or another 1 over here. How would that look like? Well, let's go through that. So we had a high voltage pulse, and we're moving from 1 to 0, so 1 to 1, so we transition to a low voltage state. That's a 0. Now, keep in mind, it's 1 to 0. 1 to 0 has no transition. So which means we're going to stay at that voltage level, at that low voltage pulse. Okay? Until we have maybe a 0 to a 1 before we transition again. Okay? We'll go through some examples that would indicate some of these later as a science assignment or illustration wise. So you can get a clearer understanding of some of these things in terms of the various techniques that are involved within the non-return to zero. But just to get an overview of that, just keep in mind that with the non-return to zero inverter, signals only transitions when you have a 0 to 1 or a 1 to 1. Any other transitions, it's not, that's not required transition, or any other changes in the bit sequence does not require a transition, meaning that you only stay, the signal level stays at wherever it was initially, but from the previous bit. Okay, but at the initial bit sequence state, notice that 0 is level and 1 is high. So assuming that the bit started with 1, then you'd have a high voltage pulse over here. And if the next one were to be a 0, then what happens? Because you have a 1, 0. Now there's no transition within 1, 0. So you just basically move on to what? A low voltage pulse to indicate the first stage of the first two stages of the signal representation at the bits levels. Okay, maybe if we start working on some illustrations or some examples of various bit sequence, then you start understanding some of these things. Okay, so that's how the non-return to zero technique really works. So as we mentioned earlier on, they are very, very popular within terminals and other devices. That is just used to interpret digital data. Okay, so let me go back to, let's move on to some of the pros and cons of using the non-return to zero techniques. Pros, they're easy to engineer, they make efficient use of bandwidth, and very uh, application-wise, I use the most magnetic recordings uh, applications. So an example here would probably be uh, a magnetic disk. If you want if information like the hard drive that you have, the your 3.5-inch hard drives, HDDs, generally uses the non-return to zero techniques for the way they interpret the signal information stored on them or transmitted across various applications that you might have. Things of read and write. Okay. The cons are they need DC components, they need power or direct current component to to help them interpret the various bit sequence that you have, which is either the ones or zeros. And since it's very simple, it's very basic in its formation, they do lack synchronization capacity or capabilities. Keep in mind uh, when you are dealing with electrical signal transmission, synchronization at the timing level, at the clocking level is very, very essential to guarantee uh, the integrity of a given information. Without synchronization, within the clocking setup, you could have a number of uh, disruption in a given signal being transmitted. So ideally, most of the non-return to zero techniques are not employed within data transmissions. Then because they're not very, very effective. Since within data transmission, uh, you'd have within high digitized data transmissions or for data signaling, you're probably dealing with a number of signal coming through a given medium. Without synchronization and at the clocking level, you'd have a lot of congestion of the signal and factors that would really impede the integrity of a given signal uh, can be seen or can be prone. So ideally, when it comes to data transmission, the no return to zero techniques are not highly employed. We'll look at much more efficient and effective signaling that are used for, or signal techniques that are used for data transmissions. Okay. Okay. So the next groupings or encoding technique we have is uh, the multi-level binary techniques. And here is where you actually do employ the the negative and positive voltage levels. So the first technique, or the one of the techniques that are within the multi-level binary encoding techniques is the bipolar AMI, which is the alternate marking version. They use more than two signal levels. If you recall back with the non-return to zero, it was only two signal level that was incorporated, either uh, a level or high, which could be interpreted as either positive or negative depending on how the voltage fluctuations are encoded or illustrated or interpreted. Okay. But when it comes to the multi-level, hence the word multi-level, we're using more than two signal levels. Okay, so here at least three signal levels are seen. We have a plus, a high voltage, a zero voltage level, and then a negative voltage. Okay, binary zeros for the alternate marking versions. Binary zeros are represented by no line signals. So the signal bit sequence or the data bit sequence have a zero is usually represented by no line signal, which is still labeled. A 1 is represented by a positive or a negative pulse, depending on how the polarity of the signal alternates. Okay, no loss of synchronization. If a signal string is long with one occurrences, then you don't have no loss of signal synchronization. Uh, this then the bipolar also one thing that it has as an added advantage is it has no net DC component to it in terms of how the signal voltage are managed or are transmitted. So in other words, it does have lower bandwidth and are easily prone to error detection. Okay. Generally, they say the multi-level binary technique is supposed to be an upgrade from the non-return to zero, non-return to zero technique. Since the non-return to zero was a much simplified signaling technique, it didn't really address challenges with various other uh, transmission applications, signal transmission applications. So they thought of another approach, and this is by using, uh, more than two signal levels to address some of the issues that comes with synchronizations within the non-return to zero. So this is supposed to be an upgraded version. After engineers realized the non-return to zero couldn't be applied to a number of applications that require synchronization at the clock level to really guarantee the authenticity or uh, the validity of a given signal, the validity of a given signal. So this was adopted, but just like any other signal techniques, there are issues as well that comes up. So hence they had to improve it, and that's where uh, the other techniques comes into play. The other higher techniques comes into play. Okay, which is I think the biphase the next one, right? Okay, so now let's look at this in the signal interpretation uh, uh, graphing, so we can actually look at understand it much better. Keep in mind there are two techniques involved in the multi-level. We did have the bipolar, and then we also have the pseudoternary. So the pseudoternary, usually with the pseudoternary binary ones, are represented by absence of line signals. If you notice, the bipolar was zero, that was represented by absence of a line signal. And the binary zeros represent alternation of either positive or negative pulses. So basically the reverse form of the bipolar AMI is what you have for the pseudotenuries. And they have no advantage or disadvantage of our bipolar AMIs. And H is the basis of some application, or H plays a huge basis for uh, other applications, some application that you might have uh, to employ within a given system. So let's look at from a plotting point. So as we mentioned earlier on, S0 is indicated as 0-bit sequence, or 0 bits within a given transmission. It's represented with a level voltage or no voltage presence, and 1 is represented with uh, a voltage presence or positive voltage presence. 0 as usual, no voltage. Now the alternation comes when you have uh, uh, and a set of ones within the bit sequence. So the first one will give you if the sequence had already had uh, a one initial start, it would have the high voltage pulse, and when you did have a subsequent one within the bit transmission, it would have the alternation. It would take the other state, which is the negative. Okay, okay. So looking at this sequence, for instance, we had a 0 1 0 0 1 1 0 0 0 1 1 1. Sorry, 1 1. So we mentioned that zeros are usually level voltage pulses, and ones are positive voltage pulses, and it applies to zeros across board. So if you know all zeros are always level voltage, the indication of an absence of voltage uh, pulse. But the ones are the indication of voltage pulses, and they have to alternate from either a positive or a negative. Okay. So since we already had a high voltage bit for one, the next one should have the alternate voltage level, which is negative, and then positive. The 0 would always be level. And then the next one, since the previous voltage pulse was positive, the next one has to be a negative. The next one has to be a positive. So a negative and a positive. Very good. Pseudoternary is practically the exact opposite. Okay? Where 0 is actually now a positive voltage pulse, and 1 is leveled. So wherever you see a 1, it's pure level. And 0 alternates now. So it's just exact opposite. If you notice, you had a plus or a positive voltage pulse, a 1 being represented by a negative, a level voltage pulse, are all more or less the term the absence of a voltage. And a 0 is actually an indication of a voltage, which is quite interesting. But that's just the encoding techniques adapted for this, maybe for specific application implementations, as we indicated earlier. And so if you go through this, you notice that you have the exact opposite, but the alternations are only based on the ones and the zeros. Okay, so alternate on ones with bipolar, and always keep zeros at level. You also know ones from either positive to a negative, positive or negative, or negative to positive, and maintain all zeros at level. And then on the pseudoternary, the reverse, or the quite opposite. Zeros are usually high voltage pulses, ones are level. And you just alternate the zeros from positive, negative across board. Okay? So generally, when it comes to maybe some questions that you might come across within this multi-level binary technique is which of the encoding techniques adapts the negatives? Sorry, adapts the 3 voltage level